We're all set. Okay, thank you very much for coming.
Sir, there's 1 second to make. Okay, got it. Yeah, we'll get to go.
Okay, welcome to this thesis defense. There will be 3 parts. First, the candidate will give a presentation. Then the general audience will have the opportunity to ask a question. Then we will ask the general audience to leave. And the thesis committee will have questions for the candidate. And then in the third part, we will ask the candidate to leave, and then we will deliberate. Please go ahead.
That's good. Thank you, Professor, for the introduction. And yeah, thank you all very much for being here in person and on Zoom. I do appreciate it all. And for those, for my family around the world, good afternoon and good evening to you all. We've got what I think is some very exciting stuff to share. We've got a bunch of results regarding machine learning. The title is long, but the words machine learning are the main things to focus on with our title. Now, to kind of understand what machine learning is, we kind of want to think of it as a subset of what we call artificial intelligence, AI. Now, AI is a word that's thrown around a lot nowadays, but the meaning of AI is when we have computers do tasks that humans ordinarily would do. Machine learning is kind of a subset of this. Now, what machine learning is more specific, is when we have models that kind of learn from data rather than being given explicit instructions. So we don't have to explicitly program machine learning models. So that's what the thesis as a whole is about. But for today, I want to narrow down the scope even further. I want to say that within machine learning, we're going to be focusing today on a certain type of model. And that type of model is called a neural network. And we're going to get into what neural networks are. So that's kind of our first slide, and let's get into it. So what we have is my clicker no longer working. Let me use that. It was working a minute ago. Oh, it's because I don't have this selected. Give me a second. Okay, here we go. So let's get into some background as to what we're doing. So as mentioned, we're looking at neural networks. And in modern day machine learning, neural networks are really good at many tasks. They're all around in our lives, and they're used for many types of tasks. Some of them may be things like speech recognition. They may be things like processing images and videos. It may be things like, powering ChatGPT. That's been a big one in recent years. Those kind of things. And so they're really good often at what they do. But there are drawbacks as well. One of the big drawbacks is that they're considered what we call a black box. And what we mean by black box is that they, it's hard to kind of decipher what exactly they're doing when we run them. You can't really explain very easily how a neural network comes to its decisions. So that's one problem. And another problem is that they're very resource intensive. You may need some specialized hardware, such as GPUs, in order to run them. So those are 2 problems that we're tackling today. We want to improve our understanding of how neural networks work. And we want to develop results that make them kind of perform better, so we don't have to rely as much on complicated hardware. So here's our agenda for today. I'm going over 3 chapters of the thesis. And we're kind of in the midst of the introduction right now. We're going to continue with this. But what we're going to do is we're going to kind of ground ourselves in a practical application where we use a certain type of neural network called a convolutional neural network. And we're going to see exactly how this works on a certain type of medical imaging task. And then after the intro is done, we're going to move on to 2 chapters. One of them is about getting faster predictions, and the other is about understanding neural networks better. So as mentioned, we're going to kind of have our introduction be this kind of medical imaging task. So as mentioned, we're going to look at a specific use case, and what we're going to look at is actually some real kind of research we did in collaboration with an industry company called Clarix Imaging. And they have some really exciting and unique technology that they produce. And what they produce is a kind of 3-dimensional scanner. And this 3D scanner is used in lumpectomy procedures where breast cancer is removed. And their technology is used by surgeons where they kind of take this removed tissue, they put it in a chamber, and it produces a 3-dimensional image of this removed tissue. What we did was we had a specific project in mind with them. We wanted to say, when we have a kind of three-dimensional scan of some tissue that was removed, we want to segment where exactly in this tissue we find cancer. So specifically what that means is we want to say, for every three-dimensional pixel, we want to label it as either this is cancer or this isn't cancer. Now, the reason we would want to do that is because this would facilitate this, fast decisions by surgeons. It would let them quickly decide, things like, do they need to remove more tissue and kind of generally assess the health of the patient. And normally, this type of task is done by humans, and it takes a very long time. So automating this would be very big. So that's our context we want to keep in mind. And what I've been throwing around a lot is in the title CNN, Convolutional Neural Network. I haven't explained exactly what that is yet, but it's something that we used in this task. What a convolutional neural network is it's made up of many operations that we call convolutions. And this is what a convolution is. It makes these convolutional networks very good at processing images. And what it does is it says it takes in an input image and it has some kernel, which is also kind of a grid. And we say, well, each possible place that we can overlay this kernel on this image, what we do is we take all these values, multiply the corresponding values together, add them up, and it gives us one entry of our output. And so that's what a convolution does. And the power that comes from this is that these values aren't fixed. When we train a network by kind of showing it what we want it to do, it kind of learns on its own what values we should put in this. And therefore, this convolution operates as a filter. And this filter allows us to kind of do various operations. It may do things like detecting or highlighting edges, detecting or highlighting certain colors, and so on. And so by having it kind of learn what filters are best to apply for specific tasks, it becomes very powerful indeed. And what a convolutional neural network is we take a bunch of these convolutions and layer them up. We put them in separate layers. Remember, for our use case, we have a 3D scan. So the same goes in 3D as well. You just take a 3D input and you have a 3D kernel. So that's kind of the building block of convolutional networks. But there are a couple of other operations I want to show as well, because they'll be relevant later. Another common operation is we might want to put activation functions on these outputs. And the most common one here is called ReLU, Rectified Linear Unit. And what this kind of does is it kind of is inspired by biological brains, where we have kind of neurons, and these neurons send electrical impulses. So they may kind of fire or not fire. And that's what ReLU kind of emulates, is it kind of says, when we have a positive value, we don't change it, but when we have negative values, we set it to 0. So that's one of the other operations I want to focus on. And one more operation is that's going to be relevant later, is something called skip connections. And skip connections are often used a lot in deep neural networks where we have many layers. And the usefulness is that if we have these layers, a skip connection just says, take the output of one layer, add it to a later layer. And the benefit of this is it allows data to move more freely back and forth, and gradients moving backwards throughout the network. It allows values to move back and forth more uninterrupted without being interrupted by these layers. So what I've gone over is 3 kind of key parts of a convolutional network. And what we did in our medical imaging application is we did make a network using these operations. And I won't go into the specifics, but instead I'll show the results. So remember, we wanted to segment cancer in 3D, and normally this is done by a human. And what I have here is a real 3D scan of some removed breast tissue. And what happens here is that we have highlighted in white here, this is a metal marker that has been physically placed in this specimen during pre-operation to denote where they determine the cancer is. The green part is where an expert has gone through and manually said that they've determined that the cancer is there. And you can imagine this has taken a very long time. And it requires a lot of expertise. Now, the really exciting part is, here's what our model did. By segmenting the cancer, it made basically the same assessment that this expert made in determining where the cancer is. And so this has a lot of potential for kind of speeding up these types of decisions. Now I'm going to keep moving on, but before I do, one thing that I want to highlight as well is that we made a chapter about a very important consideration when it comes to this. And what that is about is the question of interpretability. Like, if we don't have this kind of manual segmentation, how do we know we're getting the right answer? How do we know why this model is producing the outputs it is? So that's something else we did. I'm only going to spend one slide on it. But the question of interpretability is, do we know why we're getting these outputs? And for medicine, where it's particularly important, we really want to be sure. What we did was we investigated how, we have so-called interpretable models, and we saw, are they producing good explanations? What we did was we investigated it. We generated some data where we know kind of how to come up with the explanations, and we saw, were these explanations sufficient? But again, I'm not going to dwell on that too much for today. But yeah, that's where I'm going to kind of leave the intro, and what we're going to do next is move more into the math of this. So as mentioned, coming up, we've got two main chapters. One of them is about making faster predictions. We want to kind of rely less on expensive hardware. And another chapter is how we can get better understanding of how these models work. So we're going to move into that. First off, we're doing how we can find faster predictions. This little kind of image here hidden, which is going to give us a little preview of what's to come. We'll find out exactly what this image is saying. But I want to present to you some research questions. Two questions, first of all. One, can we represent linear convolutional networks? And what I mean when I say linear is that we're not including those red loop activation functions. Can we represent them as a single layer without losing predictive power? And another question is, can we use skip connections? Can we get their benefits without having to kind of get that computational overhead from kind of storing that output and adding it back on later? So those are two questions we're going to have a look at, but I'm going to focus on the first question for now, and then we'll get to the second one. We're trying to represent linear networks as one layer. How do we do it? Well, the key is if we were able to represent those convolutions as matrices. The way that we would do that is, if we're trying to represent a linear convolutional network by kind of taking these convolutions and kind of squishing them together, the way that we would do that is by turning them into transformation matrices and kind of pre-computing what this kind of matrix would look like. And our goal is, if we're able to do that, we would kind of say, take these matrices and we would kind of, as mentioned, pre-compute that. So how do we do that? Remember what a convolution is. It's when we have kind of a sliding kernel and we find all places we can put it over an image. What we do is, let's say we have an example convolution, and let's say we're performing it on a 3x3 image. This is what this matrix represents. And let's say we're performing a 2x2 convolution. So this 2x2 kernel is highlighting one of the possible places that this could be, that the kernel could be. And where are all the possible positions we could overlay this kernel? Well, it could be the top left, top right, bottom left, or bottom right. There's 4 possible places. And when we want to represent this convolution as a transformation matrix, each of these positions corresponds to a single row of this transformation matrix. And it kind of looks like something here where we have off-diagonal entries. And by using this transformation matrix, again, remember, we're using this on a 3x3 input. What we'd say is we take that input, turn it into a vector, and then by multiplying by this transformation matrix, we're getting the same output as if we had just done that convolution. Now, this representation is helpful for us because this kind of segues into one of our results. Here's our result. Now, let's imagine that given an input x, let's say that every layer of a neural network does this. It takes that input, multiplies by matrix A, and adds some vector B. Then what the network overall is doing is saying, multiply by A, add B, multiply by A, add B, over and over. And you can see why this is computationally expensive. But our result is that we can represent this as just a single layer by pre-computing some A and some B for appropriately chosen A and B. Now, in this case, it's a bit kind of simple because obviously A is just AN times AN minus 1 all the way up to A1. But the novelty here comes from the fact that this representation can be very inclusive of other operations. It can include things like skip connections, resizing and padding operations, which we haven't gone into, and we can represent a lot of kind of common operations that a neural network may want to do. So we end up with just a single layer. So that's our result. We have one. We can take these, we can take these neural networks and turn them into one layer. What does that mean for us? Well, to find out exactly the benefits of this, we set up an experiment, and our experiment was to say if we pre-compute these values, how much of a speed up and how much of an accuracy up are we getting? So let's test it out. A very common neural network architecture is called ResNet. It was very popular in around 2014, 2015. And the reason for this was that it utilized skip connections very well to build very deep and very powerful neural networks. So we tried out some ResNets, and what we told it to do was we tried it to apply it to this MNIST dataset. And what MNIST is it's kind of highlighted up here. MNIST is a database of digits, images of digits that have been written by hand, and we ask our model to tell us, what image is being represented here. So when we did that, our ResNet, if we represented it as one layer, it got an accuracy of 98%. Whereas the benchmark, if we use a true one-layer model, was only 88% classification accuracy. We saw a 6-fold reduction in the number of misclassified examples. That's one way to think of our results. Another way to think of our results is if we think of the speed up by representing things as one layer. Our speed up was, again, 98%. And this would vary based on the type of model. But we saw some really promising results there. That's our experiment, and that kind of ties up one of our research questions, but it will continue to tie up to be relevant as we move forward. But for now, I do want to pivot a bit to tackle another research question. Remember, one of our other research questions was, how can we get the benefits of skip connections without the computational overhead? Well, we found a method for it, and it's about removing skip connections. So what we do with neural networks is we train them before we use them. We show them the problem we wanted to solve by giving it data. And what we can do is we can say, as we show it more data, what we can do is we can weaken the strength of the skip connection. And if I draw everyone's attention to this red line here, over time, as we show it more and more data, we weaken the strength of the skip connection until at the end, we have a network that doesn't have that skip connection at all. So potentially, this can give us the benefits of skip connections without having that there. Let's see if that's the case. Do we still get the benefits of it? We're going to do that in an experiment. But first, let's see the algebra of what powers this. So normally, the way we represent a skip connection is from some layer J to some layer I, is we say that the input to that layer is given by half of the layer that came before, plus half of the layer that we're kind of skipping from. That's the input to our skip connection. But what we have is, in order to phase out these skip connections, what we did was we said, take some new variable, call it t, and replace this 1/2 value in the skip connection. And notice when t is 1/2, we get the same skip connection we started with. When t is 0, that skip connection is gone. This value fades away. And so what that means for us is that we're creating what we call a homotopy between networks with skip connections and those without. And so by kind of continuously deforming this value, we're ending up with something that doesn't have it at all. So that's the algebra behind it. But how can we use it? What benefits does it give us? Well, we tried up some experiments. What we tried was we tried various methods for taking t and setting it to 0. And what we found was that we didn't lose any classification accuracy when we did this. If we kept the skip connections in versus taking them out, we got the same accuracy. So good, we can take these skip connections out, but why would we want to do that? Well, we can measure how fast these networks are when skip connections are taken out. And in our experiments, we observed a speed up when predicting of anywhere on the range of 22 to 46%. Now, what this value was depended on the type of model, and we tried various things like various ResNets, various convolutional networks, but it gave us a kind of moderate speed up. So that was encouraging. We could take out these skip connections. So summarizing what we have so far, this is going to kind of put a bookend at this first chapter. Summarizing what we did so far, we found a method for representing linear networks as one layer, and we found a way to take out these skip connections. This first method gave us a huge speed up. The second method gave us a moderate speed up. But this does raise more questions as well. One question is that notice that the first method, this applies to linear networks, but the second method doesn't. And now there's a problem with linear networks in that they generally, not a problem, but they're generally not as powerful as non-linear ones. And so this raises the question, how can we apply both of these methods to non-linear networks? So that kind of is going to give us a hint to our next steps. We're going to segue into another chapter, and what we're going to do in this next chapter is try and solve that problem. How can we get that single layer representation on non-linear networks? Well, the key to doing that is we're going to examine what we call linear regions. And what these linear regions are kind of subsets of the input space, where if you take a small enough subset, the network behaves as a linear map. And the way that we do that is we use an existing field called tropical geometry. This isn't something we invented, but it's something that we use, and we're going to see exactly what that is. So moving forward, how can we do that? Well, we're going to explore these linear regions. Again, I have an image that's a bit of a preview here. And how can we find out exactly how to use this one layer representation? And let's find out exactly what this image is saying. So here's the research question. I've kind of already posed it, but here's the research question. Can we represent linear networks as one layer? Can we represent piecewise linear neural networks as one layer? So what does piecewise linear mean? Piecewise linear is when we have functions that if we look at kind of a segment of them, we just have a linear network. We have a straight line. And what tropical geometry does is it allows us to study these kinds of piecewise linear functions very nicely. So there's some examples here, but what we're doing today is we're only really considering ReLU functions. I just gave some extra examples, but that's the only one we're worrying about. And what tropical geometry is it has a very deep connection to neural networks. It was found by Li Wenzhang et al. In 2018 that neural networks with piecewise linear activations are equivalent to what we call tropical rational functions. Now, what is a tropical rational function? We can see it geometrically here. What it does is it says, here's an example in 2D, and if we have a 2D input space, it's kind of placing linear boundaries around each region, and within each region, this function would behave as a linear function. So you can kind of imagine the output looking like planes on each of these regions. We can imagine it in 3D as well, and it requires a bit more hand waving. But in 3D, you can imagine that a tropical rational function would kind of place walls between different boundaries. And within each of these walled segments, we would have a linear function. So that's the geometry of it. But how does the algebra work that makes this work? Well, the way that we do this is we use tropical geometry, where we perform operations on what we call the tropical semi-ring. And what I mean by this is that we do operations, but we replace the usual plus and multiplication operations with tropical plus and tropical multiplication. What that means is instead of adding two values, we take the maximum, and instead of multiplying two values, we add them. And this leads us to various conclusions. One such conclusion is that the tropical quotient is the difference of two values. So if we know what the tropical quotient is, that means that this tropical rational function is just the difference between two tropical polynomials. So how do we use that? How does that come into neural networks? Well, remember, when we represent a single layer of a neural network, again, we're saying if we take some input x, multiply it by a and add b, that's what each layer does. And in nonlinear networks, we also apply this ReLU function to that output. Now, if we take that operation that each layer does, we can represent it, and I'm not going to delve too much into this, but we can represent it as the difference of two tropical polynomials, and therefore every layer is can be represented in this way. And what we can do is we can turn this into a recurrence relation. As we add more layers, we end up with a representation of the entire network. Now, what we can do with this representation is we can use this for a theorem that we came up with. So what is this theorem? Let's imagine that we have a neural network with ReLU activation functions. Then if we take some vectors where these vectors correspond with the size of each layer, what we can do is we can fill up these vectors with entries +1 or -1. And so what we're kind of essentially doing is we're assigning the value +1 or -1 to every neuron in this neural network. Then depending on how we choose those values of +1 and -1, depending on how we assign them, it will uniquely correspond to a single linear region, and we can kind of find the boundaries of this linear region. And by doing that, we're able to do things that I'll show us, such as making visualizations. That's the algebra behind it, but kind of, again, how does this look geometrically? There's a very strange looking image here. Let me give it a moment to simmer. Okay, so this is a very strange looking image, but what this is representing is this process of finding a single linear region on a small neural network. This is representing a neural net. And what this neural network is doing is it's saying, take in two values as input, and then we have a first layer with two neurons, we have a second layer with two neurons, we have a single output. So it's a very small network. And when we want to find a single linear region, what we do is we say, first, start out with our whole input space represented in blue here. And every time we find a ReLU activation, depending on how we choose +1 or -1, we're choosing one side or the other of a given hyperplane. And on subsequent layers, we kind of intersect these hyperplanes. And again, we add in a new hyperplane every time we find a ReLU activation function. And we end up with a resulting linear region. Now, this is kind of similar to some methods in computational geometry, where we want to find intersections of half spaces. But some difficulty comes in here in the fact that the later hyperplanes depend on whether each of the previous neurons were active or not. So that adds in some extra complexity. But if we have one linear region, you can kind of see how this leads us to finding all linear regions. One way to imagine it is if we imagine what we just saw as the single leaf of a search tree of assignments of +1 and -1, we can traverse this tree and we can find all linear regions of a neural network. And by pruning it in certain ways, we can make this traversal more efficient as well. So that's what we found. We found a way to come up with all linear regions, but how does it look in practice? Well, we can set up an experiment on a very small neural network where we tell it, give it a function in 3D with x, y, z coordinates, and given these x and y coordinates, we can ask this neural network to approximate the z coordinate. And by doing this, we can see where is it placing the linear regions of this network. Well, let's try it out. Here's a some kind of arbitrary 3D function. It was just chosen because it looks cool. What we did was we asked, given the XY coordinates, can we approximate the Z coordinate? On the trained neural network, we found out that it did some really smart kind of placing of these linear regions. This is a very small neural network, by the way. So it's constrained in its resources. But in early layers, it was very smart. It placed these kind of sweeping long hyperplanes on early layers. And then later layers will kind of approximate these kind of curves that are on that lie around these axes. And so this gives us intuition as to why neural networks are powerful. It's because they're adaptable with their linear regions. If we gave it more resources, it would continue to place these, to divide these linear regions in a way that represents the underlying data. Notice a more powerful neural network would, again, even more closely approximate this underlying data. So that's one example. But notice if we change the function we're approximating to a radial function, then even with constrained resources, again, it finds a good way to approximate this. And given more resources, again, it becomes even closer to this radial function. So this was really cool. We found out that neural networks, one of the reasons they perform well, among many reasons, is because they're very adaptable with their positioning of linear regions. So that's a kind of indirect result in that we can't, directly apply it. Instead, it gives us understanding. How can we directly apply this? Well, an application of this is after we train a neural network, what we can do is if we want to get that one layer representation on any linear region, this network is behaving linearly. So what we can do is we can pre-compute the linear maps on any region. We can't do this for all linear regions because it will be far too computationally expensive. It was shown by Guido Montefort et al. That the number of linear regions is exponential in the number of layers and linear in the width of those layers. It's far too much. So instead, what we can do is we can say, whenever we find a helpful linear region where we find data, we can save that linear region for later. And what that allows us to do is it allows us to kind of save the important linear regions. So how exactly does that work? Well, remember the MNIST dataset from earlier. What we did was we took the test set of MNIST, so values that we didn't train the network on, and what we did was we made a scatter plot of all the test set values. We said, every single scatter plot here is one digit from 0 to 9. And we kind of, clustered them by similarity. And what we saw was that the trained network, these blue highlighted scatters are values where it was able to use a cached value from the training set. And what we found was that the cached values are often the values near the center of the cluster, so common values, whereas outliers near the edges of the clusters are less commonly cached. So those are highlighted in red. That was for a kind of like medium neural network. But we also found that it varied based on the size. If we had a small neural network, it would cache almost all the time. Whereas if we had a larger neural network, it was less often able to use these cache values. And so this algorithm becomes less effective for larger networks. So that remains an open area of research. How can we ensure that larger networks continue to use cached values? And we suspect we may want to use something called knowledge distillation, where we represent large networks or large models with smaller models in order to make use of this. So that's our practical application. But again, this led us to even further understanding. It led us to more understanding of skip connections. What we did was we did another experiment as well, where we examined how often do networks with skip connections versus those without, how often do each of these networks save cached values, or how often do they use cached values, I should say. Well, we did some statistical tests and we found that skip connections rely less on their cached values. And so it makes our algorithm less effective for networks with skip connections, But what it means is that these neural networks with skip connections are performing a more sophisticated operation. And again, skip connections, they're very cheap to add in. And so we end up with something that's giving us low cost improvements. Another reason skip connections work well that we found was that they have more linear regions even before you train the network at all. So just by adding more skip connections, you get a more advanced model without having to even do anything. So that's kind of the end of this chapter. And what I'm going to segue into is our conclusion. And we're going to see, we're going to summarize these things we've just seen, and we're going to see how they apply to real world scenarios. So concluding, and again, remember this image, I didn't explain what it was at the time, but now we see this was actually, these were actually the linear regions of a small neural network on yet another function. Kind of looks like stained glass. I think it's pretty cool. So summarizing, let's keep in mind our context from earlier. Our context was that we had this medical imaging task, and then we saw some various kind of, less grounded results, more kind of theoretical and mathematical results. But we can kind of think about how these would apply to this medical imaging context. The first methods we saw some various methods for getting faster predictions in convolutional networks. And the way that this will benefit us in practice is it may not be possible to use all of these methods, these methods in the first bullet point. It may not be possible to use them on a very deep advanced network like this, but the benefit it does give us is for kind of low resource systems where they can only run very simple models. So by kind of reducing the overhead there and by allowing those kinds of systems to use more advanced models, it kind of lets us do kind of maybe small tasks such as those that might be performed by systems on a chip and things like that. Another thing we saw was that we found a theorem and an algorithm that allowed us to find all linear regions of neural networks, and we visualized them. So the impact of this was that it gave us some understanding of why neural networks perform well, and it allows us to kind of foster that trust in neural networks. It allows us to say, give us the confidence that we're getting the right answer when we set things up correctly. And on the other hand, it allows us to say, if we are getting wrong answers, it allows us to kind of diagnose it or better identify when we're not doing the right thing. We also saw this method for caching maps of linear regions. And again, this gave us, this kind of unified these two methods from earlier, because by kind of pre-computing linear regions for nonlinear networks, what this allows us to do is it allows us to kind of get faster predictions on very advanced models. So you can kind of think of this as if, remember again, the kind of breast cancer segmentation, the results of this mean that we may be able to kind of use fewer hardware resources in these surgeries where we do use this, potentially reducing costs of this kind of technology. And then, maybe that cost can be passed on to the patient, insurance, or wherever those costs go. And then lastly, we found understanding of why skip connections lead to performance improvements. The reasons we found were that they give us more linear regions, and they rely less on cached values. And so that that again gives us the confidence to say we can kind of continue to move forward with kind of research with skip connections and find out more ways to kind of build future models with them. Another thing was that all of these experiments have shown the code is publicly available and it can be accessed anytime from here. So that's where I'm going to leave it. I'm going to open up the rest of the hour to Q&A. There's an interesting slide here, I think, with some of my favorite images from the thesis. But I'm always happy to flick through the slides. And once again, I thank everyone very much for being here and for their attention. And I give extra thanks to my thesis committee for their extra time devotion for this as well. So thank you all very much. And that's where I'll leave it.
So now the general audience will have an opportunity to ask questions. That includes also the general audience that is joining us via Zoom.
Could you go back to the slide where you showed the formulas for the layers of the neural networks for the topical geometry and that led to the recursion?
Yeah, absolutely. So let me go back there. Give me 1 second. So is this the slide you're looking for?
Yep.
Okay.
Okay, so the revenue function is specifically just the base case, and then the rest, like the recursion, is just more generalized topical operation.
Yeah, that's pretty much the idea. So what we're showing here, and that's a great question, by the way. What we're showing here is if we have one layer, what we would do, and I've kind of omitted some of the details here. But if we can represent this as the difference between two triple polynomials, what we do is we kind of, as we make the recurrence relation, we kind of keep track of the polynomial that's on one side of this kind of triple quotient, and we keep track of the other one, and we keep track of what their values are and kind of compute them separately. Kind of as we move forward throughout the network, we're saying, you know, how does this value here and how does this value here change? And basically, another thing that this leads to, by the way, is that if we're able to track both of these separately, the boundary of the linear regions that these create is just given by seeing where do these two polynomials kind of where do they intersect. So that's a great question. Does that kind of cover what you're looking for?
Yeah.
Great, thank you.
Other questions from the general audience? Okay, so we can conclude then this part. We will ask the general audience to leave the room.
It's been a couple weeks now.
Oh, I can forward you the thesis.
Okay, I'm back.
Okay, thank you.
Yeah, I'm always happy to kind of give out as for where specifically on the page is any of the things we want. If thank you for coming.
Yep.